Let us consider a second example. In this example, assume that your discrete time random process is a superposition of multiple purely sinusoidal signals expressed by this expression, and you see that you have different components. You have at frequency, let's say omega 1, with a complex amplitude of, let's say, A1. At frequency omega 2, you have a complex amplitude of A2, etc. So you have, let's say, a number of, and assume that x of n is wide sense stationary. In this case, the random variables AIs should be uncorrelated. This is what we have seen before. AI should be also zero mean, and in this case, you can show that the autocorrelation function, if you calculate mean of x of n conjugate, so you have a double sum, a sum over I, AI e to the power j omega I n, and then because I have a double sum, I use a second dummy variable, so I put as L, and then I get AL e to the power j omega L n, and then I have to put a conjugate on the second term. Okay, now these two sums becomes a double sum, and I could change the order of expectation of a double sum. So I get a summation over I, another summation over L, expected value of AI, AL conjugate, and then times e to the power j omega I n, e to the power of minus j omega L n. And obviously you see that these parts are not random and will simplify. And then this guy is zero if I and L are different, because we say that these guys are uncorrelated. So in summary, the result could be simplified. So what you get is that your autocorrelation function will also have a number of purely complex sinusoidals. Now, if you take the Fourier transform of that, you get some delta functions at these frequencies. So what you see is that at frequency omega I, you get a real number, which is sigma 2i, this is variance of AI. And then also this is periodic. So at frequency of omega I plus 2 pi, you get the same things and everything. And then you have at omega 1, you have another energy and so on. So the only difference between continuous time and discrete time is that for continuous time, this power spectral density is periodic. So whatever is happening in the frequencies between minus pi and, let's say, pi is replicated periodically. Now, obviously, you can write this one in Z transform, so you get Z transform of that, and you can use the expressions we had before.